Hello, in this lecture we are going to discuss about the sensors and transducers, very specific to in the field of biomedical engineering. So as we have already understood that sensors are the devices which are able to convert a signal from one physical form to electrical signals. Transducers, on the other hand, these are also a piece of instrument which are capable of transforming one form of energy into another form of energy. And in real life, you have, we can find different type of the sensors which are capable of transforming mechanical energy, thermal energy, optical energy, chemical energy, etc. Okay, so basically, transducers are energy converters, or they are also it's a kind of energy modifiers. Whereas sensors, the input is any kind of energy and the output always in the form of electrical energy. Now, if you look at any instrumentation system, measurement system, basically what the main components are, the number one is the body or measurement, whose the measurement is to be recorded or to be monitored, and these are something called the physical measurement variable. And the first instrument or the first piece of instrument to this particular measurement is the sensor, and the sensor will convert one form of energy to another form, and the output is normally called as the signal variable. And this signal variable that can be used to display by the help of a display device, or it can be connected to what we call instrumentation system or any other kind of recording system. Now, some of the basic definitions, it is bit theory, but still, that makes you the concepts, clear. So the first terminology is measurement, the process of comparing an unknown quantity with the standard of the same quantity. So it's a measurement. Basically, we just want to compare the recorded reading with something of a standard quantity or standard unit. Standard quantity. Now, the accuracy means what? How close the measured value to the true value. That is normally called as the accuracy. So the difference is normally is referred to as the error, and basically one common type of error measurement is called the absolute error. Absolute error is nothing but the distance between or the difference between the results and the true value. If they are close, then the very close to each other, then the absolute error will be less. Otherwise, there must be some gap. But most of the cases, it's good to measure, to represent the error with respect to something called relative error. Relative error is nothing but the absolute error if you are going to represent as a fraction of what you call the true value, or you are going to refer with reference to what you call the true value. So this is normally measured and referred as percentage error. Calibration is a very common procedure. Normally, we want to make sure that the measured value or the instrument has to be calibrated by applying a non-physical input and recording the response of the system. So basically, calibration means what? We want to make sure that our recorded reading or the obtained reading is close to the what you call the standard value, right? So how can you do that? We can do by calibrating the instrument by applying a non-value to the instrument, and the reading that has to be noted, so that we can make sure that the device is properly calibrated. So calibration is a very important step, especially in medical equipment, in laboratory instruments. Make sure that the system to be calibrated for a non-parameter, and we want to make sure that the observed reading is within a specified error limit. So that is basically called as the calibration. Now, another important term is called the resolution, is also called discrimination. It is a minimal change of the input necessary to produce a noticeable change at the output. This is basically called as a resolution. So how sensitive? The resolution is very similar to something called the sensitivity. A minimal change of the input that is necessary to produce a noticeable change in the output. Okay, so the meaning is our system should be capable of detecting a small change in the input. Okay, that is the capacity, or that is the capability of a instrument. Now another terminology is called the precision, the capacity of measuring instrument to give the same reading when repetitively measuring the same quantity under the same prescribed conditions. Suppose if you are going to repeat the same experiment within the same environment, or with the same system, same equipment setup, same experiment setup, if you are going to repeat the experiment again and again with short interval of time, then this is if you are getting this similar reading, then we can say that this is a precision actually. Okay, now the precision implies the agreement between the successive reading. Okay, not closeness to the true value, but the reading, whatever reading we are getting, we want to get the consistent reading again and again. It may be it may be different from what you call the actual or the true value, but whatever value we observe it, that value will be repeating again and again. So this shows the precision. Repeatability and reproducibility, are the two concepts which are very much related to what I call precision. In both cases, we are using the precision terminology. Repeatability means what? The precision of a set of measurements taken over a short period, interval of time, which means that we are going to repeat the exercise or the experiments, with some numbers, or with some parameters, but that the experiment interval is going to be as short as possible. So if you are going to repeat the exercise within a very short period of time, then if you can reproduce, if you can get the same reading again and again, then it is called a repeatable, right? And reproducibility, on the other hand, is talking about if you are going to do an experiment which is for a long interval of time. The time is like really long interval of time, and also it is performed by different operators. They are doing the experiment with different operator, and also with the different instruments. We are repeating the experiment with a different instrument, and also maybe with different laboratories. And if you can get the similar reading, then we can say that this particular experiment is said to be, or this particular trial is going to be reproducible. Okay, so there's a difference between repeatability and reproducibility. Okay, now input and output range are indicating the maximum and minimum value of the physical variable that can be measured. The maximum and minimum value of physical variable that can be measured. So that range of the maximum and to minimum, that is basically called as the input as well as the output range. Okay, this sensitivity already we have discussed, and sensitivity, that it is a change of the output of a sensor per unit change in the input parameter that is being measured. So higher the sensitivity, which means this is like a ratio. We have numerator, that is the output, and denominator is the input. And if you have an higher ratio, which means that the sensitivity is higher, which means that for every small change in the input, there will be a large change in the output. Okay, that is something called sensitivity here. Now another term is called linearity. Linearity means what? The closeness of the calibration curve to a specified straight line here. Okay, so this is basically say cal or the calibration graph. This is an ideal graph, and how close in the actual the value to what you call the ideal calibration graph, then that is basically called as the linearity. Okay, linearity is also one of the very important relation. And hysteresis means the difference between two output value that corresponds to the same input. Okay, which means that we are going to repeat the same exercise again because of the, and also sometimes we can do a cyclic loading, in the sense what, if you are applying a positive quantity, then if you are then we are applying a negative quantity, right? Then try to find out the difference if you are going to get in the output when we are feeding what you call signals or the quantities or the measurements, measurements with what you call different amplitudes. Especially in the sine also. So the cyclic means what? We are going to apply positive and we are applying negative. So we are going to apply cyclic load or the cyclic measurements to the instrumentation system, and try to find out if there is any change in the output. That is basically called as the hysteresis. Okay. Now this particular graph indicate the result, the difference between precision and what you call the accuracy. Here you can find that this is the target point, and these all black dots indicate that most of these shoots are shots are happen exactly around the target point here. But in this case, we can find that these black dots are all concentrated at one particular point, but even though there it is far from what you call the target point, but it is very highly precise. So this is highly precise, whereas this is highly accurate. I mean, not can say accurate, but not highly accurate, but it's accurate. Okay, but this is talking about highly precise. Okay, so this point indicate the mean value. So if you see here, the mean value of what you call the all the shots will be something very close to what you call the target value, but the mean value somewhere here actually. So this is the difference between precision and accuracy with reference to some diagram. I mean, in a diagrammatic way. Now, in this slide, we are going to discuss about the error and then the different types of errors here. So the errors are is basically the deviation that is measured between the measured value to to the actual value or from the actual value. Type of the errors are systematic error and random error. Systematic errors are result of many variety of factors and could be interfering or modifying variables such as the ambient working conditions such as the temperature, pressure, chemical concentration, etc. A system which is designed for a particular environment probably won't work within different atmosphere or different working conditions. Okay, so this is one of the systematic error. The measurement process changes the measurement, which means that if you are applying heavy loads, okay, and tiny loads and heavy loads, these will also create some kind of errors. And the transmission process changes the signal. For example, the signal may be affected largely by the surrounding noise, and especially if when you are transmitting the signals, measured signals, in such cases the accuracy of the system will be depending upon the noise. So this is also called the signal to noise ratio of the system. Now the human observers is also one of the point which normally referred to as parallax error. Parallax error is an error just because of the position or the orientation of the observer. Okay, so I'm going to show you some example here. So for example, in this particular case here, so we have three scenarios, and this is the actual scenario where the observer is exactly aligned to the pointer, whereas this is the observer is located on the left side and this is on the right side. In both left and right, you can find some change. In the case of left, the reading is you have an higher reading, where if the observer is on the left side, you have a lower reading. Okay, but the actual value is supposed to be 250. So it is slightly, in the case of left side, it is slightly positive, I mean slightly above 250, and when it is left right side, it is slightly negative, I mean below 250. The same thing you can observe in cars and other what you call analog instruments. Random errors are some noise or unwanted signals whose origin we cannot define. There are also some environmental noises. So that's why always it is better to keep signal to noise ratio is always far greater than 1, which means that signals should be stronger than the noise here. Now, type of biomedical sensors. The sensors are mostly classified into passive sensors and active sensor, depending upon the output, whether they are in an active form or passive form. So if it is a passive form, which means that the output will be in the form of capacitance, resistance, inductance, etc. Whereas in the case of active sensors, the output is either in the form of current or voltage. Now let's look at the main broad classification of the sensors. The sensors are mostly classified based on the basic the principle by which it works. The first thing is called the resistance. The resistance sensors are classified into variable resistances. This is also called the potentiometers, strain gauge sensors, and then we have the thermistors, the temperature resistance or the resistance temperature detectors. Now, the other type of classification is the inductive sensor. Here the principle is inductance. So there is the physical quantity is going to change the inductance of the material. So in that we have a linear variable differential voltage, linear variable differential transformer transducer. It's an inductive type of transducer. Then also we have something called variable reluctance, reluctance transducers, which I'm going to discuss. So the next type of sensors are the capacitive sensor. Here the physical quantity that is being measured is going to make some changes on the capacitive parameters. Okay, and here we have parallel plate capacitors, we have the electric mic, and these are the different type of sensors which we are going to discuss in detail. Now the other type of sensors are photosensors. Here these sensors are used for transforming photo or the light into electricity. Okay, there are many type of sensors are available, which include the photodiodes, the light dependent resistor, which we also call as LDR, photo transistors, photovoltaic cell, and so on. Same way, there are other type of sensors which are very common and very potential sensors. They are called the piezoelectric sensors. They are capable of transforming the electrical signals into mechanical vibrations and vice versa. Now let us see the variable resistance type of sensors, which convert the displacement or motion into resistance changes. Okay. Now there are different types are available depending upon the use. There are depending upon the input as well. So we have linear type and angular type. Linear type, you can see from this particular diagram, this is a linear type where you will find there is a resistive element where it's like like a linear plate. Okay, you can find there is a plate here, and over which there is a part is going to move here. Okay, so we have a wiper which is attached, and we have a shaft here, and this shaft will be moving along the what you call the resistive element, and resistive element is to be in the form of what you call a rectangular plate. So here what is going to happen, the linear motion that can be converted, or the linear displacement that can be converted into change in the resistance here. On the other hand, if you see here, this is an angular sensors, or the angular resistance sensor, where the change that is going to take place, the physical input is supposed to be in the angular motion, and this angular motion is converted into electrical resistance here. So both these type of sensors belongs to the passive, because the reason is the input is what you call the physical displacement, right, either angular or linear, but the output is in the form of resistance. Now this particular linear sensors, the resistance sensors, can be converted into an active by adding some bias voltage here. So by adding some bias voltage E, we can get the change in the resistance sensor due to the physical movement into what I call electrical signals, into the output voltage. So here it's simply acting as a potential divider, where the input resistance of the input stage will be xt, the total resistance, whereas this is supposed to be xi, and this xi is depend upon the physical motion or the physical dimensions. So this output voltage will be a fraction of what we call the input voltage, and the maximum voltage we can get here is E, and the minimum voltage we can get it is it's like 0, and depending upon the position you can have any what you call voltage, and that is nothing but a fraction. So normally the fraction is ranging from 0 until 1. So you may find any number from any voltage from 0 until 1 that can be obtained here. Now in this particular case, we are talking about the same principle, but it is working in an angular way. The resistance orientation is in an angular fashion, and again we are using a bias voltage in order to get the output. So here the input will be theta, the angular displacement, and that is going to change into the output voltage here. So now the next type of sensor is the strain gauge. It also belongs to the variable resistance sensor, and this sensor is capable of transforming strain into electrical resistance. So before we discuss into the structural details of the strain gauge, we'll have some basic understanding about what is stress and strain. So basically stress, it's indicated by sigma. It's nothing but the force applied in Newton per area. Okay, normally unit is in a Newton per square meters. So the force applied divided by area is basically called the stress. So the corresponding, when you apply a force on a particular material, correct, or load on a material, the material try to stress, or the material try to withstand the applied force. That particular internal force is basically called as the stress here, and can be measured by how much force you apply divided by area in square meters. Now, when you apply a force, definitely there will be some kind of change in the dimensions, and this dimension change, which we are going to represent with respect to the original dimension, that is normally called as the strain. So strain is nothing but the effect of the stress here. So when you stress the material, then there must be strain here, and the strain is indicated by epsilon. Epsilon is equal to del L divided by L. It's also called del A by A, or maybe del D by A. Okay, there is no unit because it's all ratio. So what is del L by L? It is either you can reflect the strain in the along the length. So that's why change in length to the original length, or could be like change in the area to the original area, or could be change in diameter, depending with respect to the original diameter, right? Now, there is also another term which is a constant for a material called Young's modulus, and the ratio of stress to strain, the ratio of stress to strain, normally called as the Young's modulus. Okay, so these are the basic understanding of the strain gauge, and with this, we'll discuss about how a strain gauge works. So basically, it's a tiny wire which is held under tension. It gets slightly longer, and its cross-sectional area is also going to be reduced, right? This change its resistance is proportional to the strain or the sensitivity of the wire resistance. So what is the basic construction? You can find that this is the strain gauge. There is a tiny, very tiny, wire is, connected between two terminals. And normally this particular device, or the sensor, is attached to a specimen under strain. So what happens when this particular specimen is strained, or you apply some stress on, what is going to happen is that along with this particular material or the specimen, this is going to be strained, or this is going to be stretched, or you will find some changes in the dimensions. It could be in the length, or can be radius, etc. Accordingly, there is some minute change in the resistance value, and that resistance value is directly proportional to the change which happens on this particular specimen. So normally that sensitivity of that strain gauge is normally denoted by S, and that S is calculated as follows. So before we discuss that, this is the physical form of practical form of strain gauge, and the strain sensitivity, which is also called the gauge factor. This is the two terminologies. Either is strain sensitivity or the gauge factor, and the gauge factor is given by del R divided by R, the whole divided by del L by L. So this is basically the numerator indicate change in resistance to the original resistance, which is a unitless quantity, and the denominator is del L by L, which is nothing but change in length to the original length. So they are, both are ratios, and that's why the gauge factor normally is a unitless quantity. Now as such, we saw the strain gauge, and the output will be change in resistance, while the input is like what the corresponding strain. Now in most of the practical cases, we want this change in resistance to be reflected as output voltage. So in such cases, we can connect, the strain gauge is part of a circuit. Normally we call it a bridge circuit. So here you can find there is a 4-arm bridge here, and in this bridge, one of the resistance is acting as the strain gauge here. So what is going to happen when the bridge is balanced, perfectly balanced, then you will get 0 volt across the output here. But if any reason, if out of these 4 resistors, one resistor is the strain gauge and others are the non-fixed value resistors. If one of the resistor, which is the strain gauge resistor, is changes because of the strain applied, then you will find some change in the output, and that output change is directly proportional to the change which happens on this particular strain gauge. Now there are many applications for the strain gauge in the practical field, and one of such application is the blood pressure sensor. So in blood pressure sensor, the minute change which happens in the blood vessels, that can be easily measured by using the strain gauge. Same way, you can also use the strain gauge for the breath sensor. It can be used for displacement sensors, force sensors, weight sensors, etc. So there are many applications for the strain gauge in the practical practical field. Next, we are talking about the temperature sensor. There are different type of temperature sensors are available in the market, and one of the common type of sensors normally is the resistance temperature detector. It also belongs to a category of PTC, because if you are using metal as a temperature detecting material, then the corresponding change of resistance with respect to the temperature, which will be a positive temperature. So that's why these type of sensors is also called PTC, positive temperature coefficient of resistance. And the resistance of a metal that can be calculated by the equation R is equal to R0 into 1 plus alpha into T minus T0. So where R0 is the resistance at its standard temperature, or maybe zero temperature, 0 degrees centigrade, or any other reference temperature, into 1 plus alpha means it is a constant temperature coefficient of resistance, and T0, T is actually the measured temperature, and the R0 means the reference temperature. So this particular reading is based on a reference temperature. So for example, if you are considering 10 degree is the reference temperature, then this is supposed to be 10 degree. Then the actual temperature could be 20 degrees. So in this case, we'll have 20 minus 10, that will be the temperature difference, that is multiplied by a constant called alpha. Then that is going to add 1 multiplied by the value of R0. R0 is nothing but the resistance which is corresponds to the reference point here. Okay. Now this device can be used to measure the output, but here again the output is in the form of resistance, right? So in order to measure, this is on a digital device, definitely this output reading we have to transform into current signal or voltage signal, and by using some kind of associated circuits here. There is another type of sensor, temperature sensor, is called the thermistor, and from the name itself is clear that it is the two terms. One is called therm is the thermal or the temperature, and the remaining hysteresis stands for the resistor here. So it is nothing but a thermal resistor, and they are also very commonly used in our field. And there are different type of sensors, the thermistors are available in the market. Okay, so now the thermal thermistor resistance of a thermistor that can be calculated by using the relation R equal to R0 into e to the power minus b or beta into 1 by T O minus 1 by T. So here R0, as we have discussed already, it is some standard reference temperature, the resistance at standard temperature, or any other known temperature, that is R0. In this example, R0 is with reference to T0. Beta is a factor, that is a constant for a specific thermistor, and T is the the temperature that the actual temperature that we want to measure it. Okay, so T0 is the reference temperature and T is the actual temperature, and the change is going to reflect on the resistance here. Now, depending upon the response, like whether they are responding positively or negatively, we have two type of sensors available in the market, which are PTC sensors and NTC sensors, the positive temperature coefficient sensors and negative temperature coefficient sensors. Okay, the only difference both of them are one is changing with respect to positive. So as the temperature increases, the temperature is also increased. So you can see here in the case of PTC, as the temperature is increases, the resistance values also increases, right? Whereas in the case of NTC, it has got a very high resistance in the beginning when the temperature is very low. As the temperature increases, the resistance drops. So there are practical applications for these type of NTC and PTC thermistors. Next device is called the thermocouple. So thermocouple is basically a couple of two different substances or two different materials here. Okay, so what you can see here, we have using two different material. One is a material A, and other metal is like B. So there are two different metals. Okay, for example, you can use one is like copper, and could be one is like constant Dan. Okay, so either copper, constant Dan, or any other combinations. We are going to use one element here, one material metal A, another metal B, and we have got two temperature here. One is called the lower temperature, sometimes is also called the reference temperature, and the other temperature is called the higher temperature, which is supposed to be measured. Because of this temperature difference, then it is amazing to note that there is a potential that is generated, and that is first found by Seebeck. So that's why it's called Seebeck effect. Okay, now according to the Seebeck, when there is a difference in the temperature, and because of some Seebeck coefficient, you find some output voltage here. Okay, now how we are going to use this device for the measurement. So for example, if you are trying to measure the temperature of inside a furnace or some very high temperature that is to be measured, then here we are using the copper constant and as the basic material, and one junction, one point, because we have got two junctions here, blue color indicate the constant and the red color indicate the copper. So one of such joint, we are going to keep as reference temperature by using some kind of ice bath, by keeping the temperature is somewhere around 0 degrees centigrade, whereas the other temperature, other point, we want to keep at the temperature of the sample or the temperature that is to be measured. Now, because of this temperature difference, you will find some output reading here, and that output reading is directly proportional to what I call the temperature difference. Now, this is a practical device. You may find it in the market. So, it can be used for measuring very high temperature here. Okay. Now, the basic equation is the output voltage is equal to a factor S, which is the Seebeck factor, multiplied by Tx minus T reference here. Tx is the temperature that is to be measured, and T reference is the reference temperature. Okay, it could be sometimes it can be 0 degrees centigrade. So now we are talking about the inductance sensors. Here again we said the physical quantity that is being measured is going to change the inductance of the material, and the inductance are different types. The inductance are classified into self-inductance and mutual inductance here. So from the graph it can clearly clear that there are two set of coils are here is connected. So if we are interested, we have got one set of coils, and that can be design in this particular pattern, and you can find that there is a metallic core is inside. This part it's nothing but the metallic core. So by moving this metallic core up and down, is it possible to generate some EMFs here? And what we have found that the inductance of the coil or the voltage induced in a coil, that is depending upon the position of and the particular core here, and also it's also depend upon the speed or the velocity of the motion, etc. So there are many factors which also depending upon the number of turns here, it depend upon the size of the core, depend upon the magnetic permeability, and so on and so forth. Now another type of sensors is called the mutual inductor. So here we have using a single set of coil here, but here we are using two set of coil. And what we are trying to do, we are going to make a change in the voltage because of the change in the voltage happening in another coil. So what you can see, we have a set of coil here, AB here, one set of coil, and CD is another set of coil. We are changing the voltage in this particular coil, which is AB, because of the effect called mutual inductance. And since they are these two coils are situated next to each other, what is going to happen? The change in the first coil will impact or will introduce some change on the in the coil C and D. As a result, some voltage will be induced, and this type of inductance normally we call as the mutual inductance here. So this type of coils that can be used for measuring what you call the linear as well as the angular type of measurements. So basically these are the sensors that can be transformed the mechanical vibrations into electrical signals. And one of such the sensor which very commonly used is called the LVDT. LVDT stands for Linear Variable Differential Transformer. So what you can see here, there are four basic terms. Linear means what is used for the linear motion. Variable means the output will change. Differential means you can see that there are this is a kind of transformer. This transformer has got a primary winding and there are two secondary winding. The specialty of this transformer is the transformer core, the core which connect between the primary and secondary, the metallic core that can move, or this is like a a mobile type of what you call core. And the output of the secondaries, they are connected in such a way that the output will be always the difference of V1 minus V2. That's why it's called differential. So linear, because of the linear, it can be used for linear measurement. And variable means the output will normally change. Differential means the output is normally the connected in a way that the output will be always a difference, because V out is equal to V1 minus V2. Then let's just suppose that the coil is exactly located, the core is exactly located in the middle, exactly in the middle where it is completely linked with what you call these both the secondary coils equally. As a result, what we can find that in the voltage which is induced in the coil number 1 and coil number 2 exactly same, and the output will give you a 0 reading because V1 minus V2 is equal to 0. Now on the other hand, if you can see in this particular image, that this coil is located extreme just with linked with only the coil, top coil, and it is away from the first coil. As a result, this voltage will be higher, which means in this example V1 will be higher than V2. As a result, V1 minus V2 will give you some number, and that number will be proportional to the position of the coil here. So by this method, and on the other hand, if you are moving this is to the other side, all right, we will have an opposite nature here. So by this way, any voltage, any position of what you call the core will give you a corresponding change in the output in the form of either positive or negative voltage. Okay, so this particular device is used in many applications where you can measure the vibrations, you can measure the displacement, etc. very accurately. And the next type of sensor is the capacitive sensors, and from the basic parallel plate capacitor rule, C, the capacitance of a parallel plate capacitor is calculated by the equation epsilon R epsilon 0 A over D, where epsilon R is the relative the permittivity of the medium, and epsilon 0 is the absolute permittivity, which is normally constant. It is 8.85 picofarad per meter. A is the area of the plate. In this particular example, if you look at this is the area, then if you multiply it by the length by breadth, you will get area of the the cross-sectional area, and D is the distance of separation here. So by varying the distance separation, or what you call A, or maybe sometimes even by changing the epsilon R, it is possible to change the value of C here. So if you are interested to measure a physical quantity, that physical quantity is going to change any of these parameter, either epsilon R or A or D, and by this way it is possible to measure what you call the C value. So there are many applications for this type of sensors, and this is used for a linear type of capacitance, whereas this is used for an angular change here. So the difference between these two, both are capacitance sensors, but this is used for linear motion, and this part is used for what you call the angular. So these are the main type of the sensors. So hope you have a better understanding of different type of the sensors. And the next class I'm going to introduce some of the practical applications of these type of sensors. Okay, thank you for watching. Thank you.